All right, let's get started. So I apologize for being out last week. I got taken down by the flu pretty hard. So I hope people watch the chapter 17 videos. And that being said, though, chapter 18 does build upon chapter 17. And then I tried to print out at least like what I call the cheat sheet for chapter 17. So I printed out this rate loss summary table, which is basically all you need to know, right, for chapter 17. It summarizes the order, what that means, right, your units of K, which is helpful, your rate law, and then the half-life expression. So anytime you see the word half-life, then you want to use these formulas and then, right, base it off of the order. And so we can kind of go back to chapter 17 if we need, but I just kind of want to at least start moving forward with chapter 18. And so a couple of notes. I actually forgot to calculate the average for the exam, but I was pretty pleased with it. There was like a nice grouping of people that did really well and then like pretty decent scores. That being said, there were some people that did not do that well. So I was thinking about offering test corrections for 70%. So if you got, of course, greater than that, then you don't have to do corrections. Otherwise, you can test up to 70%. And since my exam is out of 110, I believe that comes up to about 77 points or lower. So again, if that applies to you, I'll hand out the exams probably like during the midpoint. And so then you can either, like I said, correct up to 70% or otherwise I was pretty pleased with the scores. And then of course, don't forget your paper. So a few people have asked me for some feedback on their papers, so that's excellent. So I will, I'm happy to give you feedback. So the earlier you get a paper to me, then the easier it is to give me some feedback, and I could probably start accepting papers for credit. So just don't forget about that. And I'm happy to meet with people individually, so you could set up individual appointments would be my suggestion if you want extra help with that. And then the plan for lab is I just want to squeeze in last week's and this week's lab, or at least that's kind of my plan. They're both kinetics labs, so it should be a lot of fun, and I think we'll have enough time to do it all today, or at least Tuesday can tell us how it goes. All right, so let's start diving into 18, but like I said, ask questions, especially if you're confused about 17. We can always pop back over. But basically, the whole point of 17 was to tell us, okay, well, we got this rate law, right? And we're monitoring this reaction, and we have to monitor it, right? So that's really the key of the rate law chapter. And then this chapter is like, we have to determine these things experimentally. And then, so the next thing that we're doing now with chapter 18 is, okay, well, based off of our rate law information, what is the mechanism? And so that's what we're getting into a little bit of today now with our mechanisms. And, honestly, you can find like a lot of great papers out there, so not to go like down the rabbit hole, but this is a lot of like what cool OChem is what I call it, right? Like they do isotopic labeling, and then you can, watch your reaction products. You can monitor how changing things, changes your reaction rate. And again, that helps elucidate the mechanism. And so like we've seen, we have our chemical reactions, right? We have our reactants and our products. And then we're just trying to figure out, okay, well, again, what's our mechanism? And so let's think about how this might occur, right? So we've kind of talked about this where, okay, the reaction has to have some sort of collision or maybe something, is splitting apart in our mechanism. And so the point of this first statement is the probability of having three molecules colliding at the same instant, and it mentions this whole proper orientation. So this is something, right, that's really important to chemists. So you have to have your molecule in the correct orientation And if we really wanted to get bored and into the literature, right, there are whole papers on this. I actually did a summer of doing oriented molecule research, and I was like, oh, this is not for me. But the whole point of that is, right, so you have to have a certain orientation, it has to hit, and then it has to have, right, the correct activation energy. So it mentions, right, overcoming that energy barrier. But all this is saying is, okay, usually when you have a reaction, three molecules colliding at the same time in the proper orientation is pretty rare. And we're not saying that we can't see this, but this is just saying, okay, when we look at our mechanism, that usually these reactions occur in a small series of steps of maybe 1, 2, or like I said, maybe 3, but pretty rare. So that's all that that is saying there. And so again, right, we're going to look at these kind of series of reactions, kind of determine what's a fast step, what's a slow step, get our reaction mechanism. And then the whole point is that we then compare it to the rate law, right? And so basically, our mechanism that we propose has to agree with our rate law there. So that's, right, kind of our check and our powerful step there. All right, so now we're just looking at our reaction here. So we have H2 plus two equivalents of iodo-chloride give us 2 equivalents of HCl and iodine. And then we have, right, our proposed two-step mechanism here. And so we have, right, our initial reactants. So hydrogen reacts with 1 equivalent of our iodo-chloride. And then we make, right, 1 equivalent of HCl. And then we have 1 HI. And so we'll kind of put some labels on these, right? And then this goes on, our HI. And so this reacts with now our next equivalent of iodo-chloride, right, to give us our product, and then iodine there. All right, so let's look at what this is saying. And so now we can define what HI is. And so looking at our mechanism, right, so HI, it's not in our overall reaction, right? It's not a reactant, it's not a final product. And so instead, this is considered an intermediate. And I believe, so it's defined down here, right? So materials that are produced in early mechanism steps and then our later reactants in later steps are intermediates. So again, right, they don't appear in our overall reaction, but there's just some sort of immediate state here. And so again, just kind of noting this, just breaking it down. So we have HI is our product in step 1, right? It's a reactant in step 2, so it gets consumed in the middle. And so, right, it's made and consumed, so it does not show up in our overall reaction then. And so we'll get to this, right, what this means and how we put this in our rate law then. And so again, like we should have seen from our rate law chapter, so this is just kind of a repeat here. And so again, we're trying to figure out, right, what these reactants are rate law wise. And so, right, the number of reactant particles in any elementary step is called its molecularity. And so if it's unimolecular, we'll have 1 particle. Bimolecular could be 2 particles, could be the same particle, right? So A and A. And then, right, a termolecular step. So this, again, would be rare. But again, 3 particles colliding simultaneously. So again, right, this is pretty rare, but we'll still be aware of it. And so then, right, each little step in our mechanism then is like its own little reaction. And so, right, every step technically has its own activation energy. So that's something else that if you were looking at a detailed paper that they might break down activation energy of each step. And then this is where we're kind of going, our own rate law. And so again, I think we're going to see this like 100 times. So the rate law for an overall reaction, right, must be determined experimentally. So again, that was chapter 17, essentially, is like we have to have the data. We have to have the data. Okay, so now that we have the data, well, now we can figure out our rate law and then determine if it matches. And so this is how we break it down. And so this is just definition here on this first reaction, right? So we're saying that our rate of our product here is defined by our concentration, so K1, right? So this is just rate. So K1 for this first reaction, and so that's equal to, right, our two reactants. So what's coming together by our elementary step, right? So it's dependent upon our H2 concentration and then our iodo-chloride concentration. And so this is just like math right now. And then we're just saying, again, by definition, so our rate of our product for our step 2 is equal to K2 times our HI, right? So our intermediate here times our iodo-chloride. And so again, right, we're just kind of going through really simply right now. Again, just showing our molecularity, right? So this is kind of implying that these are bimolecular steps here. Again, we have to still compare it to our rate law, so we're not there yet. And so this is just kind of showing an example, again, of all our different possible rate laws and what that would look like, right? Whether we have a unimolecular step where it's first order, maybe it's bimolecular, right? That would give us second order for A. Or we could see it, right, again, two different products like A and B, or again, all these three permutations. So again, AAA, so that would give us A to the third order, or AAB, again, if they were all colliding simultaneously. So, right, this is what it's saying, that this is colliding simultaneously, so that would be A squared B, and then, right, again, three different products, be A, B, C there. Okay. So are we with me so far on this? So we just kind of defined everything, right? We still haven't confirmed anything with our actual experimental rate law. And so now we're kind of getting to it. Okay, so this is, again, right, each step broken down. But now here is, right, kind of the trick. Well, the rate determining step is going to be the slow step of the reaction mechanism. So usually in some reaction, right, you have some step. We don't know what step it is necessarily, right? It could be the first step, could be the second step. But one of these steps is our rate determining step, meaning, right, that it occurs slower. So if it's our second step, right, maybe the first step goes really fast, boom, and then our second step is the one that's actually our rate determining step, right, and that, again, is going to be shown in our rate law. And so the trick is, of course, that our product production cannot occur any faster than our slowest step. And so, right, this step determines the rate of the overall reaction. And so, right, why this is, it has something to do with activation energy, right? We can get into catalysts, how we lower the activation energy, creating a new pathway. But, right, okay, so that's what we're saying. So we have some rate determining step, and again, this is going to match with our rate law. And so our rate law then of our rate determining step determines the rate law of the overall reaction. Okay. So we're still, like I said, just getting there slowly. All right, so let's look at our next reaction here. And so we're looking at this reaction. So we have nitrogen dioxide plus carbon monoxide give us nitrogen monoxide and CO2. And then so we are given our observed rate law, right, of, okay, some sort of rate, and looks like it's second order with NO2, okay. And so then we have a proposed mechanism, again, based upon our observed rate law. And so this is what they propose. So they said, okay, well, maybe NO2 has to react with NO2, right? And so they're proposing that it makes, notice, right, our intermediate here. So we make this intermediate NO3 species. And then, so we make one equivalent of NO. And then, again, what they're giving us is this is a proposed slow step, right? And then this doesn't necessarily matter as much, right? Because it's not the rate determining step. So even though, again, we can write it, right, mathematically, so we can say, okay, well, the second step is dependent upon my NO3 reaction with my CO to give us NO2 and CO2, right? This is fast, so it is negligible. And so then, right, well, now we have to kind of verify this. And so the key here is the rate law of the first step is the same as the rate law of the overall reaction, right? And so now we can kind of verify this. And I know they've written it out for us, but right, that's what we're checking here. Okay, so looking at our proposed mechanism, so if this is a slow step, right, it's just dependent upon these two equivalents of NO2 reacting with each other. And then, right, that gives a second order with nitrogen dioxide, which does match, right, our observed rate law. So for here, for this instant, right, it's pretty simple to see that our first step matches, right? It matches our observed rate law. And so everything, again, makes sense, right? And so this, again, while we can write it and quantify it, this is not part of our observed rate law. And so then this is something that we're going to check too for this chapter. So again, we're just validating at this sense. So like trying to prove a mechanism. So this is why I was saying like this is where you get pretty creative mechanism studies, right? So then we're not really proving a mechanism, right? We're just kind of showing that it's consistent with the rate law. But to really prove the mechanism, that's where, again, these isotopic labeling experiments come into play. Like, can you isolate intermediates and all these sorts of, again, experiments. But what we're just trying to prove is, right, do our elementary steps sum to our overall balanced equation, right? So that's just like basic step 1. And so going back to here, right, does that give us our overall reaction? And so you could cancel out your intermediates, right? Verify. And okay, so we do get, so cancel out everything that's the same on both sides. And so we do get, right, our overall reaction up here. So that's just first step, okay. And then second step, again, like we're starting to see, so our rate law predicted by the rate determining step must be consistent with the experimentally observed rate law. So questions so far, right? So again, so this is kind of simple since our first step is our slow step and is our rate determining step. And so now let's look at, well, what happens, right, when we have a fast initial step and then our rate limiting step contains intermediates, right? So that's really the tricky part of this chapter is that we want, right, our rate law to reflect our reaction. And so we'll have to do a little bit of substitution to just rewrite this. And so the key that we'll use is this. So right when we have a previous step is rapid and reaches equilibrium, the forward and reverse reaction rates are equal. So our concentrations and reactants of products of the step are related and the product is an intermediate. And so then, right, we'll be able to substitute this into the rate law and get it in terms of just of the reactant. And so we'll go through that together. So let's look at our example here. All right, so now we're looking at our mechanism. So now we have our dimerization reaction. So NO, so it looks like two equivalents of it, right, dimerized to give us N2O2. And it says that this is fast, right? So that's not our rate limiting step, but we can still write, right, our rate law for this. So we'll do that in just a second. And then, so looking at step 2, what they propose, right? So now we have our intermediate here. Our N2O2, right, reacts with H2. And so that's part of our issue, right? So now we need to quantify this in terms of our reactants. And so, right, we can at least appreciate how we get this flow rate. So we're just basing it off of the reactants, right? So that's just shown here that our rate is, of course, whatever rate constant K2 is. So these Ks don't matter so much. And then, so reactants, so H2 times our concentration of N2O2. And so that gives us our rate. And then, right, our subsequent third step is also fast. And so let's figure out how to verify this. And so the other piece of information that we're comparing it to is that we're given, so again, this is our overall reaction again. So we have two equivalents of H2 plus two equivalents of NO give us water and N2. So going through that, and then, right, we're given our observed rate law is H2 and then NO, so it's second order with NO. And so let's go through how we write this. And so it's sketched out over here, but let's rewrite it together. So right, for our step 1, we can just write our rate law. And so, right, we said, well, my rate forward is the same as my rate reverse because, again, they're fast. And then this is our fast step, so we're limited by our step 2. So we can say, okay, well, we have two equivalents of NO there. So that's where we get our K1 times NO times NO, which gives us NO squared, is equal to the reverse reaction, which we'll just define since this is our first reaction. It'll be K negative 1 for reverse direction. And so that's equal to K negative 1 N2O2. Right? Does that make sense so far? And then, so from step 2, so we can just rewrite this again. So, right, our step 2 was our slow rate. And so our slow rate, right, is K2 times H2 times N2O2. Okay, so, right, all we've done is kind of rewrite this so far. And then, okay, that's our issue, and why we need a substitute is that this is an intermediate, right? So we don't have this in our rate law, so we can't just leave it there. So instead we can substitute, right? So let's solve for N2O2 now, right? So based off of step 1, we can solve. And so I'm just going to divide everything by N2O2. And so this gives us K1 over K negative 1 times NO, and then, right, I'll just square it, right, since there are two of them. So now we have this expression, right? And so now we can substitute back in. For step 2, right? So now I'm just rewriting step 2, but now defined in terms of this, right? And so now we give us for step 2. So now this simplifies to K2 times H2. And then all these K's, right, we can just simplify to an overall nu K. So NO squared. And then just kind of rewriting. So then this is just nu K times H2 times NO squared. And then double check, does that match our rate law? So yes, right, we were given it in terms of H2 and then second order with NO, which like we have shown, right, matches our substitution. So based off of that fast step 1. Does that make sense to everybody? So a few no's, but we probably just need to do this again. So let's look at, hang on, I think I threw, my notes are a little funny. So we have, so now we're shown this. So here's our proposed mechanism. And then I forgot to give us our rate law. So we have our reaction, so 2 equivalents of ozone. So that's O3. Sorry, let me rewrite that 3. Give us 3 equivalents of O2. And so our observed rate law for this is K times ozone squared. And then this is interesting. So O2 to the minus 1. And so let's check this out. And so again, we want to see, does it add up? Basically, does this agree? So I'll say, does this match? All right, so first thing we do, right, so go back to your proposed mechanism. Make sure that it first even agrees with what they're showing us. So kind of eliminate everything that's the same on the reactant and the product side. So you are left with 2 equivalents of ozone, and you get 1, 2, 3, O2. Okay, so that's okay, right? So we just are making sure that our mechanism adds up to our overall equation here. And then so let's go through our mechanism again. And so let's start. So we always start with our step 1, right? So again, we have a fast first step. Really, our rate law is dependent on our slow step, right? But we can't just express it. So let's look at a few different things. So for step 1, right, we're just given that K1, so going in the forward direction, is just equal to ozone, right? Because that's our only reactant for the first step. And then that's equal to, again, we said it's equal to the reverse direction. So K, -1. And then again, I'm just multiplying my 2 products that are shown here. So O2 and single oxygen. So I'll just leave that for now, right? We've just written our rate laws. Now I'm just going to rewrite it for step 2. So again, just showing our rate. And so now K2, since again it's step 2, so we'll just call it K2. So it's equal to our ozone times our oxygen intermediate, right? And so now here's our problem, right? So we have our oxygen radical. So that's an intermediate. So we can't just leave it like that, right? So now let's go back to step 1. Notice we have, right, our oxygen radical up here. So we can rewrite this, right, in terms of this. So now just algebra at this point. So I'm just going to divide everything. So I'll rewrite it. So K1 times O3. So I'm just trying to divide. I just don't want to do it too quickly. So then divide by this. So then I'll rewrite it. So K1 times O3 divided by K negative 1 divided by O2. So that gives us, right, our substitution for our oxygen radical. And then now we can just substitute this in. Right, so now we're going to sub this back into step 2, right, so we can get our rate law not in terms of intermediates. So that's all that we're doing, right? We can't leave just an oxygen radical. That doesn't match with our rate law. And so now I'm just substituting this in for step 2, right? So taking this. So I'll just rewrite it for a second so it's clear. So now substitute all this in. So now we're given, and again, all these K's will just make our new K. And so now we have ozone times O2 minus, and I just rewrote it like that since it's divided, right? Same thing. And so now substituted. Oh, and then, sorry, I skipped my ozone. And so now rewriting it. So it looks like that gives us ozone squared times O2 to the negative 1. And then yes, right, double check. Does it agree with what we were given? So it does, right? They gave us that it was second order with ozone, and then to the negative 1 order for O2 there. So yes, it agrees, and we determined it. Do we all follow that? So we're just substituting, right? So it's just algebra. The whole thing is, right, we just can't leave it in intermediate. So all we have to do is just algebra, right, solve for our intermediate in terms of starting materials or products, and then again compare to observe rate law, right? Yeah.
When you substituted, why you didn't like put it as a fraction form?
Oh, I just didn't feel like it. I mean, you got to get used to seeing it in either way, right? Negative 1 or over 1, like.
Are we always assuming that those reactions are like in equilibrium?
So if it's fast, yeah. So that's the whole point of it being fast is like, yes, it is in equilibrium. Oh, yeah. Yeah, it's just because this is like the fast part though, right? So it's like, it's fast anyways with that activation energy. So like, yes, what you're thinking is correct, but like why it's just so reversible is like, because it is a small fast step. So yeah, like it probably has a pretty low activation energy. So that's not, yeah, that's why it's happening fast. But yeah, fast, again, always implies the equilibrium condition so that yes, you can make that assumption. But yeah, anytime you have a slow rate, then we have to redefine it.
The exponent of negative on the diatomic oxygen?
What do you mean?
Like does it mean that we have one O2
Well, I mean,
with the rate law? For example, the ozone it's to the power 2, and then the O2 is to the power negative 1. So I'm asking, what is the negative 1 for?
yeah, I mean, it probably implies that it slows down, so that it's like right inversely proportional. So as you make more, it's going to slow down the production. So yeah, as you form O2, that slows your rate law is the implication.
Can I ask like a conceptual question? So like it has to be, the fast stuff has to be in equilibrium so that you can solve for the intermediate part that isn't in the overall formula.
Correct. Yeah.
And then you solve for that in terms of the other reactants and products.
Yeah.
So that you can substitute it in and write your rate law without the intermediate.
Exactly. Yeah. 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 So like, Ellen re-summarized it really well, but like that's the whole point. Is like we can't have our rate law with intermediates in there, so we just have to substitute to put it in terms of products and reactants, right? Because again, that's the data that you're going to be given is like whatever data, it's going to be in terms of products and reactants, so not intermediates. So yeah, that's why you bother to rewrite it. All right, so let's look at other relationships. So I think this will come up in lab too, or there's all sorts of different forms of this equation. And so now we're actually kind of quantifying this effect on temperature. I think in like first quarter or maybe Chem 104, if you've had Chem 104, there's like this general, oh, we increase the temperature by 10 degrees and it doubles the reaction rate, blah, like a really loose condition. But really, we can quantify it with our Arrhenius equation here. And so we have obviously changing the temperature changes our rate constant of our rate law. And I think we'll see this in lab today. And so we're given that our rate is equal to, so A is just our frequency factor, so a constant. So A times e to the power of our negative EA, so our activation energy goes up there, divided by RT, and now we are back in energy land, which means we're using the energy gas constant for this equation. So star that, whatever you need to do, right? Okay, now we're using 8.314 joules per Kelvin mole for our Arrhenius equation here. And then temperature in Kelvin, as we are hopefully used to using for these different equations. Right, so looking at our, and so like you guys probably know, so looking at our activation energy, so there's an energy barrier to almost all reactions. And so our activation energy is just defined as the amount of energy needed to convert our reactants into the activated complex, or right, our transition state. So again, this is just kind of like our high energy intermediate state. And then our activated complex is our chemical species with our partially broken and partially formed bonds. And so this could be something like if you were doing an organic reaction, when it's like in our weird flipping state, so one's coming off and right, like this bond's being broken, this bond's being formed. I kind of drew that terribly. Let me try to draw it a little better. So sorry, trying to show that we're like breaking X and forming Y, right? So that's our transition state, high energy. And again, right, implying that you're making and breaking bonds in this transition state. And again, that's why it's considered high energy, since it's kind of this, again, transition state. All right, so let's look at this. So this is pretty cool. Oh, I forgot to pull up some stuff. There's been so much crazy stuff that's been happening. Let me see if I can find it. Anyways, they made like new CP compounds, like ferrocene analogs. I was gonna show you guys, and now I forgot. Well, I'll try to find these papers in the meantime. But what's pretty cool, and this kind of goes back with our MO chapter, is you can have these interesting ways for these complexes to kind of bind and flip. And so this isonitrile group does this. And so, right, it's pretty interesting what this isonitrile can do. And so just kind of comparing reactants and products before we even get into what happened. But notice initially, right, it's bound by our nitrogen to our methyl group. And then what can kind of happen, and obviously in this case, right, it's more of an activated transition state, but you can find that these like alkenes or alkynes and even like benzene, but they can bind in different manners. And so what this does is now it's bound kind of side on here. And so this is a higher energy form. That being said, right, again, this is kind of what these molecules can do with metals. It's kind of cool. And so it can actually flip. And so this is considered, right, our higher energy transition state, this weird side end bound complex. And then notice how it flips to where now it's bound to our carbon there in our final product. So that's pretty interesting. So that's what that isonitrile group does. So you can see this transformation in chemistry. And then just kind of, again, defining our reaction and what we're looking at. So, okay, our activation energy is defined as, again, reactants versus activation energy, so here to here, right? And then our frequency, so this would be how people measure like turnover rate or success of catalysts. Sorry, I was distracted. I was trying to find my ferrocene compound still. And so frequency, this could be like amount of turnovers or like, so how I've done this before is like you can measure nitrogen and how much ammonia is made by some sort of frequency turnover rate. And so there's a special ammonia complex that you make and then you measure it and then you cry when your frequency turnover rate is irrelevant. No, I'm joking. But basically, frequency is just the number of molecules that begin to form the activated complex in a given period of time. And so again, right, if you were trying to do some sort of cool catalytic activity, you're comparing it to some standard. And right, you're trying to obviously get to a certain frequency, so that would be a cool breakthrough or not. And then it's just showing, again, our energy profile for this isomerization and just showing, right, our CN bond weakens and it's enough to rotate. And again, right, there is bonding activity between that. So it does allow it to kind of side end with that activated complex. So, right, it describes it as a partial bond there. And so, like I said, we can quantify this. So our Arrhenius equation, so we can find our exponential factor. So it's just a number between 0 and 1. And so we'll see another form of this equation, like I said, that will be kind of more helpful. But that just represents our fraction of reaction molecules with sufficient energy to make it over the energy barrier. But like I said, you usually be doing kind of like a 2-point form of this graph. But then just kind of things in general, so the higher our energy barrier, then obviously the fewer molecules that have sufficient energy to overcome it. And again, that's something else that you could quantify if you were interested. Again, like what is the activation energy? What is the orientation? And then we have the extra energy then comes from converting the kinetic energy of our motion to our potential energy in our molecule. So, right, again, ideally, and this is shown here, that your product is more thermodynamically favorable. So that's, again, kind of what it's implying, right, that you're going to create a more thermodynamically favorable product, sometimes called our thermodynamic sink, right? And so that just kind of means, too, that you could heat the crap out of it, as scientifically known, and then, right, it should all convert to your thermodynamic product there. And so, like I said, we'll look at another form of this equation in lab. But basically, as we increase our temperature, that increases, right, our kinetic energy, as we know generally speaking. And so then, right, increasing our temperature will then increase the number of molecules to overcome our barrier, and then obviously increase reaction rate. So again, we can summarize and quantify all this. Let's see. So blah, blah, blah. So now we're just kind of saying, right, we're comparing our thermal energy distribution. So again, saying our frequency factors, the number of times we achieve our successful turnover rate. And then our exponential factor is, again, whatever fraction of that approaches are successful. And then, of course, right, increasing temperature will increase the amount of successful turnover. And so that's just what's shown here, right? So basically, there's our activation energy. And then again, right, probability distribution. So showing our energy. And of course, right, kinetic energy, 1/2 mv squared. And then just saying if we could just take a snapshot simultaneously or instantaneously, right, some of them will be at a sufficient velocity, which means, right, sufficient kinetic energy to make that activation energy. And so what we're comparing is, again, right, our distribution. So notice, so T2 is higher, right? So it gives it a wider distribution curve. So it's just because you could still have, right, something not moving at some instant, but you have, again, a wider spread, since you will have things that are moving faster, right, with that higher temperature. And then just showing the area under that curve, right, which again is implying higher temperature, more successful collisions. Let's see. I'm still trying to find the correct new sandwich compounds that are out there. Yeah, probably. Yeah, let's take our break. I'll pull up the papers. I was still trying to find them, these sandwich compounds. I was. So yeah, I just handed out the exam for people online. So if you didn't get your exam, come see me. If you haven't taken it, please take it ASAP. They are waiting for you in the testing center. I'll give you guys another minute or two to look at those, and then we'll. Yeah, you can keep them. They're for your learning pleasure. And obviously, don't go showing them to people who haven't taken the exam. Okay, your exam's waiting for you. I handed back the exam, just FYI. All right, as we kind of come back from break. So yeah, I found the two papers that I was super excited about. These are probably also just like my favorite topics. But this one just came out last week, so February 20th, hot off the press. And then I know we've talked about these ferrocene compounds. So if you recall, actually, I have another paper pulled up. Sorry, now I got too excited. Oops. And so often we look at these ferrocene derivatives, and so this is actually another new paper that was not the one that I was looking for, but just kind of exciting. So right, we've seen these ferrocene compounds, or at least they're pretty common in inorganic chemistry, and then obviously you can put all sorts of cool things on them. But what was really cool is that they finally made the first copper metallocene complex. And so, right, you can make the sandwich compounds of all the other guys, but they didn't have the CP sandwich ones. And so you have, this is CP, the cyclopentadienyl. And so those are that weird little 5-ring thing going on. And so sometimes they have methyl groups. So CP, oh gosh, sorry. Yeah, thank you. So cyclopentadienyl is just this thing. So the CP anion here. Other times I've also worked with like CP star, it's called, and that would just have a methyl group on there. I don't know if I could find CP star though, searching for it. I could draw it for you. And yeah, it looks just like this too, these sodium CPs, very nice reagents to work with. But basically they made the copper compound, which was pretty cool. So that was hot off the press. And then another relevant article kind of with all these things. And speaking of CP, and this was huge. So of course this goes back to, right, we usually we give our Gen Chem spiel of, oh yeah, carbon makes multiple bonds, blah blah blah, single, double, triple, and then we say something of like, oh, silicon can't really do the same, or at least not as well. But of course, chemists are always trying to push silicon to be kind of more like carbon. And so that's what was really cool about this paper that also came out recently. So this was at the beginning of February, but they basically made a CP ring with silicon. And so that's pretty cool. And so the work, if we scroll down to the pictures here, the pretty pictures. So this is the pretty picture of what they made. So again, that's just like the CP ring. So, right, CP would just have carbon, 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 carbon. And then, like I mentioned, usually methyl groups or whatever other substitutions you want to put on there. And so this is huge that they made a ring with silicon doing that structure. And then there's a crystal structure of it shown over here. Again, right, nice pretty pictures to verify what you made. So that's really big. So that's why this was in Science too. So that's huge, making those bonds with silicon. And then this is also just kind of, again, pretty pictures to look at and kind of understand like where the future is, right? Like, so again, the whole point is we're looking at these crystal structures. So like you have to grow a tiny little crystal. That's where they shoot the X-rays at it, right? And then, yay, pretty picture of what we're actually made. And then what you can also appreciate, right, is they did some sort of DFT calculations, right, like calculating the energy of all these states. Notice they have the HOMO-LUMO gap, right? I always mention the HOMO-LUMO gap. That's, again, what researchers care about. And so they have that, again, calculated there. So, right, highest occupied, lowest unoccupied. And, I mean, we won't get into the weeds of this paper. Yeah. Well, the X-rays, remember, just like show the diffraction pattern of it. Yeah, so like back when we like briefly talked about the diffraction pattern, like that's how it works. So yeah, you shoot your tiny crystal, and then it gives you like this diffraction pattern. And then unfortunately, like I said, I never took a course in this, but basically it's like, yay, do math and use a computer and solve it. Some people know how to solve crystals by hand. Like I said, there are only so many courses you can take in your life, and I didn't take that one. But yeah, I didn't set out to be a crystallographer, so maybe I should have. That's another discussion. I mean, that's basically it. I mean, there are like other arguments. So I think like the HOMO-LUMO gap of silicon is a little bit bigger too, and for whatever reason that can lead to like instability. Yeah, yeah, they're just like tricky to synthesize. Um, I'm not sure if people have like the complete answer to as to why it is so much more difficult, but I mean, you can at least kind of appreciate the synthetic route. Oops, where's the synthetic route again? So that's what's kind of like cool about all these papers is just like the route to get there. And so you can kind of appreciate the synthesis, right? So they make a straight chain thing, and then eventually they get it to kind of start ringing. And then this is weird. I'm not sure like why that happens, but that's kind of interesting. And then then they have this like weird structure here, 7, and then notice, so this KC8 here, that's just potassium basically, but it's intercalated potassium, so they do a reduction. So adding electrons to it to make that ring. And then it somehow kicks off the chloride as well. So right, you can see that in the reaction, but I mean, really, really awesome synthesis, honestly, to get that. Kind of tricky. Anyways, I can always post the paper later, but yeah, that's always fun. And then personally, I like making the CP compounds. Those are always fun as well. So, like I've made like iron CP benzene. Those are great starting materials. I've made like trimethylvinyl silyl cobalt thing, where it's basically this compound, CP star. With a trimethylvinyl silane group on there. But anyways, let's go back to our Arrhenius 2 point. So back to this. And so basically what this is used for is, so we have two different factors. And like I said, I think this will come up in our second lab today with our iodate reaction, our kind of clock reaction. And so we can either throw it into this Y form. So looking at this version of our Arrhenius equation, so we have, this is our form y equals mx plus b. And so, right, we could graph this. And like I said, I believe we do this in lab, if I remember correctly. But you can graph then our natural log of k, so our rate versus 1 over time, and get our straight line. And then, right, calculate for our slope of our line to get our points there. And then, right, so our y-intercept is the same as the natural log of A. A has our same units as K. And then again, right, X is 1 over T. Y is natural log of K. So that gives us a form. The other form, which, like I said, maybe we use this one. I don't quite remember the lab that well. But this is another common form of the equation. So, right, we have some sort of rate at one temperature, our rate at our initial temperature, and then just make sure that you keep T2 with K1, right, and then T1 with K1 here. And so this is probably the form that you'll use in lab or in practice problems. So probably that 2-point form. But all of these could be relevant. All right, so let's try our 2-point form equation then. And so now looking at our reaction here. So we're given our nitrogen dioxide, and carbon monoxide gives us nitrogen monoxide and carbon dioxide. And so, okay, hint that this is going to be our 2-point, right? So we're given a rate constant at 701 Kelvin is measured at 2.57 per molar per second. And then at 895 Kelvin, it's measured at 567 per molar per second. So find the activation energy. So see if you can plug that into your formula. Don't forget, right, R is 8.314 for our energy. We're in energy land. The R is the 8.314, since now we're in joules and energy. So make sure we're using the other gas constant. Yeah, so T2 would be the second one given here. But like I said, it doesn't matter who's who, just like keep K2 with, yeah, T2 with the respective temperature. Yes. So R is, it does have the unit of joules. So yeah, let me sketch out the work and you guys can tell me whether you agree. So yeah, just plugging it in. And again, right, this is natural loss, so K2, just make sure, okay, big number is equal to, so solving for EA, 8.314. Oh, and then, sorry, I need to get my calculator. And so just make sure you're testing out your calculator, right, that you're in the correct base. Should be natural log. So I just plug this in to solve, so 5.39. So I'm just algebraing away. So what do we get for our activation energy? Oops, I screwed that up. Okay, so I get about that answer for my activation energy. So that's in joules. So about 144, or let's see, I'll round it to 145 kilojoules for the activation energy. So double check your math if you didn't get that. Or questions? We get it? All right, looks good. So let me know if you have other questions or issues, or you can always see me after class if you have calculator punching issues, but I think it should be pretty straightforward, again, just as long as you're in the natural log and everything. And we'll do this, like I said, in lab as well. All right, let's see. I think we did this one. Yeah, I knew my notes were a little scrambled. So let's look at kind of the rest of the chapter. Maybe we can finish the chapter and then that'll leave Thursday for just kind of more practice. And so then just looking at our chapter, so it mentions catalysts. And so the thing about catalysts, right, is usually it makes the reaction go faster. So we usually call this like a positive catalyst. And then especially my biologist in here. So what would be a negative catalyst? What's the other term for that maybe you hear more in biology? Yeah, inhibitor. Is that, can't remember if it's on our chemistry. Yeah, so our chemistry might neglect to say that. So I'll put that. So inhibitor. So that would be considered, right, a kind of negative catalyst, again, where it is kind of competing for the activation site, we'll say. So that's kind of the difference. And so then catalysts, this is obviously a very big and broad topic. So like we mentioned, usually when we say catalyst, we're talking about a positive catalyst that is going to affect the rate without being consumed. So, right, this also means that it can have kind of a lower loading, meaning that we don't need, right, 100% of a catalyst, a 1-to-1 ratio. So usually you can do like 5 to 10% loading is kind of in general what you see, especially for like those palladium catalysts that you will probably use in OChem. And then again, they provide a complete alternative mechanism. So I should have gotten up some papers here, but I'll try to pull up some catalysts so we can again kind of appreciate the alternate pathway and what that means. And then, right, catalysts could be consumed, but then they are made in a later step. So kind of what this is implying with our ozone reactions. So it's saying, okay, our ozone reacts with some chloride radical in the atmosphere, makes oxygen, and then this CLO intermediate species, right? And then that can go on to act as our intermediate catalyst here. Let's see, why can't I just find a good page? And then, so then there's two main types of catalysts. So a homogeneous catalyst would mean that all species are present in the same phase. And this is personally the type of work that I consider like what I do. So I would be considered a homogeneous catalyst where like everything I make is in solution. Now I'm getting too excited. So let's look at, are you guys familiar with these Grubbs catalysts at all? Here, this is what I'm looking for, just like the basic Wikipedia page. So these Grubbs catalysts are pretty famous. So they're used as catalysts for olefin metathesis. And this guy, I can't remember if he passed away now. I used to know him. He's actually an old professor that I know. So he's a professor at Caltech. Oh, well, he's dead now. My bad. So he did pass away, but very famous guy for making these olefin metathesis catalysts. And so what's really cool about his catalysts is that even though they are what I would call kind of like designer catalysts, and now we kind of get into like, is this catalyst even like reasonable? So I would say like my research was probably not reasonable catalyst, right? In the sense that like I was never going to make a catalyst that we would put in a bottle and sell. It's just like it was way too complicated. But what's beautiful about these catalysts is like, yes, you can buy them, you can then use them in your reaction. And so these were the early versions. And then of course it got a little bit more complicated. These second generation here have these carbines to stabilize them. So those are pretty famous. But again, like it's super cool that you can like purchase them. So now people like literally just buy these catalysts, put them in their reaction, and they work. And so I was hoping, and so kind of this is at least like a small appreciation of just showing you again how it creates a whole new mechanistic pathway, right? So the whole point of these Grubbs catalysts is that this olefin comes, it binds to the metal, new mechanistic pathway, and then spits out, right, this ring closing metathesis here. And so again, right, the whole point is just completely new pathway with these catalysts. So that's pretty cool. So kind of the problem and issues. And so the other issue with this homogeneous catalyst is like recovery could be difficult of the catalyst. And so again, that's a beautiful thing about the Grubbs catalyst is you buy it and then I don't think you recover it, but it is cheap enough where that makes sense. Again, that's where you're going to want like a lower loading because again, obviously you don't want to use a 1-to-1 molar ratio of these catalysts that you're probably going to throw away. Unfortunately, again, for the homogeneous catalysts, that's just the nature of the workup is again, right? How would you recover it? Not saying it's impossible, but like I said, usually it doesn't happen with homogeneous catalysts. So then that brings out the entire field of heterogeneous catalysts. And so this is going to be like your car catalytic converter. And, you know, a lot of people could argue that better methods, and there's, again, that's why they steal your catalytic converter. A little too easy to recover. But, right, basically, that has a lot of, again, implications in industry that make it a lot more favorable. So a lot of industry people are more focused on heterogeneous. I would say I was a more theoretical, fun chemist. No, I'm joking. But anyways, that's kind of the difference. And blah, blah, blah. So there's kind of pretty pictures of that. And again, right, of homogeneous where they're in the same phase. So this is showing gas, but often, again, we see a lot of solution chemistry. And just trying to show the illustration. So again, a homogeneous, they're all going to be kind of in the same phase. I would think of that more solution in different solvents, right? Organic solvents, whatever. Versus heterogeneous, where you have, again, some sort of surface that is primed. Again, right, people are trying to burn and synthesize different materials or grow them or something, attach something to the surface for your heterogeneous catalyst, and then, again, your either solution or gas phase reaction will come along. And so these hydrogenation reactions generally occur catalytically. So like I mentioned, you'll probably see some palladium on carbon in your organic future, assuming you guys are going to take OChem. And so again, this hydrogenation reaction is very common, and you will see it. You will do it. You will do it catalyzed. And so again, you can just kind of appreciate how our catalyst, again, provides our surface for our reaction. And then moving on to enzymes, again, just an overview. I'll leave your catalyst for your biology classes for the most part. But again, right, these biological catalysts are very specialized with our enzymes then. And so, right, generally these are protein molecules that are then called enzymes. And of course, those are very specific to our enzyme and substrate, right? Very lock and key. The other thing is just keep in mind about, right, like denaturing proteins. And so, of course, that destroys the protein folding, right? So depending on how it's denatured, so you could denature with heat, right, or acid-base reactions. I think generally acid. I'll put base as an aside, but right, changing the pH is anything to kind of disrupt that folding, and then that denatures your enzyme. And again, okay, so we've seen this, right? Our simplified lock and key model, again, just showing that our enzyme substrate is very specific. I think you maybe know that from biology. Well, now I'm going to go off. Right, so you have like catalase, amylase, right? So all those break down. So catalase breaks down carbohydrates. I forgot what amylase does. You guys help me out there. More starches, thank you. I'm not the greatest biologist. You can tell I'm an inorganic chemist, or maybe you guys can't tell. I get too excited with metals, but that's okay. I'm not excited about proteins, but they're also way harder to crystallize in all fairness, so they're not as exciting. So, okay, blah, blah, blah. All right, so let's see, I'll probably save the derivation. So we're going to do a derivation of this enzyme substrate, but I might save that for Thursday. All right, let's kind of look at your homework and kind of see how we feel. Okay, at least we went through that chapter kind of quickly. So I guess before we dash off to 18, was there anything on 17 that we need to kind of look at in more detail? We kind of went through 18 pretty quickly, but like I said, that's fine because we can save Thursday for kind of 17 and 18 issues. So yeah, I'm just trying to look at chapter 17. And so really, again, chapter 17 isn't too difficult. It's just like literally data and analyzing data. The first part could have been tricky, but again, this is just trying to get you to see how to quantify the rates, and then to be consistent, right? It had you put the substance 1 over your coefficient. Again, that's just scaling, right? So again, like stop me, or like I'm just trying to hit an overview for 17. I'm expecting that people watch the videos, but I just want to make sure we kind of at least somewhat know what's going on. And then 17, again, right? This is just 18 and 17 really go hand in hand. And so we're just saying, yes, we have to measure the reaction rate. These are all the monitoring techniques, which I would get way too excited about. So NMR, spectroscopy, right? So you can do all sorts of different things. So obviously this is very experiment dependent on what you're looking at. Then again, or you could, so sometimes you have to take aliquots. So that would be like if you don't have a good way to just like do live monitoring, then unfortunately you might have to like take a sample out, maybe have to do a mini workup, and then, right, see how your reaction's going. It again just depends. Gas chromatography is just a quick, easy way to get concentrations as well. Good for quick monitoring, potentially by aliquots. So aliquots, like I said, this just depends whether it needs a workup or not, really. And so that just means like, is your sample ready to go, or is it maybe in a salt form, and that's why you would have to do a workup, and then it would be in the neutral form. So blah, blah, blah. So right, all chapter 17, like this is probably the biggest summary of chapter 17, right? Determine your rate law experimentally. So you can't do anything without data. Okay, so maybe let's look at this. Let's just make sure we can do the practice problem together. And kind of the idea, because you'll be, like I said, you'll be doing this in lab too. And so look at our data here. And so we're looking at our reaction of, again, nitrogen dioxide, carbon monoxide. This is another theme of these chapters, all these like dimerization reactions. And so, right, given this data, what is our rate law? So go ahead and kind of look over that. Like I said, if you've watched the videos, maybe you already know the answer, but just want to make sure we're all on the same page. And what do we have to do too to like compare? Oops. Sorry, I had audio off on my recording for a while. I probably sneezed and then forgot to undo it. My bad. I apologize. So then natural log, and then we have a negative sign, so that makes sense. Times -1. Sorry, just trying to get rid of this sign. Then divided by 1.44, or 1.4 times 10 to the -7. And so then we have our t, and then it is in seconds, right, given our answer, or our rate. And so then 1, 2, 3, 4, 5, 6. And so that's about 4.0 times 10 to the 6 seconds. And I'll just leave it in those units since.
Just try to go back to the cheat sheet. I wanna like ask something about it. So is it any different if I use the first or the second equation, or they're just the same?
You mean like this one?
Mm-hmm.
Yeah, you could probably use this one. You're just going to end up throwing it into this form to solve it. So that's just why I put it like that, right? They're all the same form.
Simplified version of the first equation? Okay.
Yeah, it's just manipulated to help. All right, that's probably it for the day. All right, let me know if there are other questions. Like I said, we can do problems from 17 and 18 on Thursday. We'll do the derivation. I apologize again about the audio for hitting pause. I wasn't paying enough attention. I need you guys online to help me out with that. All right, again, let me know if there are questions, and we'll just keep kind of doing more practice problems on Thursday. All right.
Hi, did you get a chance to print out the research, or should I come another time?